Hello everyone. We now come to a new topic that is an extension of the self-inductance. It is called mutual inductance. Okay. Slightly now things will become complicated, but then if you have been following all the previous lectures, this will be very easy for you to understand. Okay. So think about now the concept of mutual inductance. Let's say I have one common core. So on this core, there are two windings. So this is the first coil, and there is another coil. So this is coil 1 and this is coil 2. Okay. So now I want to define something called mutual inductance or M. Okay. So what I am to say is mutual inductance, that is flux linkages produced in coil 2 due to current in coil 1. Okay. So let me explain that. Imagine that there is a some kind of voltage and then some current is flowing here I1. Because of I1 there will be a flux phi 1. Now this flux which is produced in this core, it is assumed that the flux is not leaking outside the core because core offers a low reluctance path and this entire flux is linking throughout the core. So therefore by definition the flux phi 1 is linking with the coil 2. Okay. So although phi 1 is because of I1, okay, so it is linking with coil 2. So we ask the question, what are the flux linkages in coil 2 because of the current in coil 1? Okay. So if I increase this current, so by increasing this voltage, if I increase, so if I1 increases, then phi 1 increases, and as a result, the flux linking with phi 2 also increases. Okay, so if I assume this is N1 turns and this is N2 turns, the product N2 into phi 1. Okay, this is flux of the first coil linking with the turns of the second coil. Okay. This will be proportional to I1. So again, you know why? Because I1 and phi 1 are proportional to each other. Therefore, if I now look at it from the point of view of the second coil, then I have it like this. Now, what is the constant of proportionality? So N2 phi 1 is equal to M into I1, whereas M is nothing but N2 into phi 1 by I1. So what is the unit of M? So nothing but Weber turns per ampere. So this is exactly same as we had seen the unit of inductance. Okay. So therefore, this is like you can consider it as the first method of defining mutual inductance M. So what is it? It is the flux linkages in the coil 2 because of the current in the coil 1. So if you imagine that statement, then you can naturally write M is into phi 1 by I1. Incidentally, at this stage, this is just for review. So there will be inductance in the coil 1 also. So that is N1 into phi 1 is the flux linkages of the first coil. So this will be proportional to L into I1. So whereas L, if you want to know, then I can just ignore this I1. So L is nothing but N1 I1 by phi 1. Or more famously, L is nothing but N phi by I. So this is what we learned in the case of self-inductance. Just extension of the concept where there is a possibility of flux of one coil linking with the other coil. Now this formula is true only when the entire 100% of the flux phi 1 is linking with phi 2. Sometimes there might be some kind of leakage. So locally some kind of flux might only link with this one and then may not link with the other two. In that case you can always multiply with that factor, maybe 20% or 40% or 90% of flux is multiplying with it and then still find M. Okay. So when the situation comes, we'll deal with that. Okay, so this is the first method of defining mutual inductance. Now, what is the second method of defining mutual inductance? Now, this is basically geometrical. So remember, again this is review. What was L based on geometry? Nothing but n square into mu naught mu r into A by L. Okay. This is definition of self inductance based on the geometrical properties of the coil. This is the number of turns in the coil. This is the relative permeability of the core material. A is the area of cross section of the coil and L is the length of the coil. Now we are coming to the something called as mutual inductance based on the geometrical properties. Okay, so what do we have here? So if I just go back to the same figure, okay. So there is a coil one. So this having n1 turns. So from the relation between, just by studying, forget about second coil, just only study the first coil. So what do we get? So now the flux in the first coil is nothing but the ampere turns of the first coil divided by the reluctance of the first coil. So this is nothing but N1 I1 divided by reluctance is what? So L by mu naught mu r into A. So this whole thing is the pertaining to the first coil. Okay. Now from this I1 I'll bring to the other side, and then this term I'll just bring it to the above. So just simplification. So phi 1 by I1 is equal to, so this denominator I'll just take it to the numerator, N1 mu naught mu r A1 by L1. Okay. So this is about, this is just a simplification. Okay, now what I want to do is on both sides I want to multiply with n2. Okay, so n2 I multiply here and n2 also I multiply here. Okay. Now you look at this term. What is this one? This is nothing but mutual inductance. This is numerator is the flux linkages because of the flux in the first coil linking with the second coil, and I1 is the current in the flux. So this is nothing but M. So therefore now I got a equation for M in terms of geometrical parameters. Okay, that means the length of the coil and number of turns in the coil and so on. So this is my M here. Okay. So more famously it was written as N1 N2 into mu naught mu r A1 by L1. So that is it. This is the second method of defining what is mutual inductance M. So here mutual inductance M, this is the first method, that is N2 phi 1 by I1, and whereas this is the second method. So naturally, as you might recall from our previous videos about how we define self-inductance, there is a third method also. Okay. So let's write the third method. So third method of defining M. Okay. So what is the third method of defining M? So go back to the first method. So I have M is nothing but N2 phi 1 by I1. So I'll just write that. M is nothing but N2 phi 1 by I1. This one I'll write it as M into I1 equal to N2 into phi 1. This one I differentiate both sides with respect to d by dt. So differentiate with respect to dt. So again differentiate with respect to dt. So M is a constant because it's a coefficient of mutual coupling. So because both the coils are assumed to be stationary, so because these are all statically induced EMF we are studying, so therefore M is a constant. So I get di1 by dt is equal to, here N2 is also again a constant, number of turns in the secondary, that will be d phi 1 by dt. Now I could put a minus sign on both sides, just simply multiplying with minus on both sides. Now you look at this one. What is this one? This can be defined as mutually induced EMF. mutually induced EMF. So this is the unit of this will be in volts. So this is EMF induced because of rate of change of current in the first coil, EMF induced in the second coil. Okay. So that is nothing but minus N2 into d∅1 dt. This is nothing but rate of change of flux linkages because of the first coil into the second coil. Okay. So this one also is nothing but mutually induced. Basically, both are equal. Okay. So the definition is normally it is d∅1 by dt into n1, that is mutually, that is self-induced EMF, whereas d∅1 by dt into n2 is mutually induced EMF. Because of the rate of change of flux linkages in the first coil, how it is linking with the second coil and how it is changing. Okay. So I can overall I can write it something like EMF mutually induced is equal to minus m di1 by dt. Okay. So this is the equation for mutual inductance. EMF induced due to mutual inductance. So if you know this quantity and if you know di by dt, then you can find what is m. Okay. So this is again the third method. So let me summarize all the three methods that we have discussed. Okay. So first method is mutual inductance is nothing but N2 phi1 by I1. That is the flux of first coil linking with the second coil divided by the current in the first coil. This is M. Another way to define M is nothing but N1 N2 mu naught mu R A1 by L1. Okay, this is based on the geometrical properties. Again, the mutual inductance, or this time we'll write it, I can write it this way. Just from this, it's nothing but EM by minus minus di1 by dt. So this is nothing but here mutual inductance. That is mutually induced EMF is nothing but mutual inductance is nothing but mutually induced EMF divided by minus di1 by dt. Okay. So these are the three formulas that three ways to understand what is mutual inductance. Okay. So based on this, let's solve some problems so that we'll get more better understanding. See you in other videos.